Hello, Momentum. Welcome to Don't Drop Acid, Transactions in Distributed SQL. So here we are again. You're starting a new project or refactor, and you've reached the point where you need to think about the database. Which database am I going to use? Am I going to keep using the one that we've always used? We're going to try a new one. You take the blue pill. You stick with the relational database that you've always known, and the story ends there. You believe what you want to believe about NoSQL. You take the red pill and you go down the NoSQL rabbit hole and see how deep it goes. And there are a lot of reasons that most of us still take that blue pill over and over again. Maybe because it is the right tool. Maybe it's because the corporation says we have to. Maybe it's because the last time I researched NoSQL years ago, I found it lacking. Or maybe I don't want to give up the expressiveness of the SQL language that I've used for such a long time. And maybe it's because, and this is what I want to focus on today, is that it doesn't have ACID. Specifically ACID transactions. So how could it possibly be any good? And the response from NoSQL advocates like myself has been something like this. Don't try to bend that spoon. Don't treat NoSQL like it's relational. There is no spoon. You probably don't need transactions. And I think there's some truth to that, and I'm going to talk about that today. But what if I told you that many popular NoSQL databases already have ACID transactions and have had them for a while? So today I want to take you inside a sparring program. I want to talk with you about what ACID means, talk about the challenges of doing it with NoSQL. I'm going to cover the reasons why ACID transactions may not be as big a deal as you think, but I'm also going to show you what the ACID means and how NoSQL databases have been adding transactions to distributed NoSQL databases. I'm going to dive deep on one of them, Couchbase, because I think it's a remarkable approach that stands out from the rest, and it helps demonstrate the trade-offs. You're going to learn the kung fu of ACID, Mr. Anderson. So these are questions I often ask myself, so I put in a slide to remind me. I'm Matthew Groves. I'm a developer advocate for Couchbase. I'm an MVP, a Pluralsight author. I've got a great family. I'm here at Momentum, so if you're watching this somewhere else, definitely check out momentumdevcon.com for all the latest on Momentum. Also, before I get started, just want to make sure you know that Couchbase is not CouchDB. Two different things. I get that question a lot. Here's my agenda for today. I'm going to talk about transactions in relational. We're going to have a little bit of a refresher. And I'm going to talk about why people use NoSQL in the first place, why it exists, what are the benefits. And then we're going to talk about what ACID actually is and why is it hard. I'll show you a demo of a NoSQL transaction in action. And then I'll wrap up with some more resources and places you can go to learn more about ACID. Okay, so let's talk about transactions in relational. Third normal form is the way we build schemas in relational databases. So even if you've never heard that term before, if you're using a relational database like SQL Server, MySQL, Oracle, or so on, you're almost certainly designing your data this way. So I'm not going to go into all the details here. And in some situations, you may even be Boyce Codd normal form, or even fourth or fifth normal form in some situations. But just to review, part of third normal form is that it must be at least in second normal form, which must be at least in first normal form, etc. Now this table here isn't even in first normal form. We've got this, what's called a repeating group of fields here, item 1, item 2, item 3. So intuitively, you see what the problem is with this. What if I want to buy more than 3 items? If I buy less than 3 items, am I just wasting space, etc.? So a more correct design for this in a relational database is to split the shopping cart data into 2 tables. Each item gets its own row in a separate table. And there's a foreign key, that's that cart ID column there, with a value that points to the row that it belongs to in the other table. And so this is how we would go about then saving a new shopping cart to the database. And it's modeled this way in the database. So let's go through each step here. First of all, we're going to insert one row into shopping cart. And so that data shows up there in shopping cart. There's probably more information, but just the date and the ID for now. We're going to insert one row into shopping cart items. So we've got that phone case that we bought. And the foreign key 100 points to that shopping cart 100. Insert another row into shopping cart items. This is the charger cable. Again, pointing to that shopping cart 100. And we're done now, so there's finally a commit. So we've finished the transaction. Let the database know we're done. Okay, we're done working you can end the transaction right here. Unfortunately, that's not always how things work. So let's try it again and see what happens. We're going to save a new shopping cart, go through the same steps. Insert one row, there's the data. We're going to insert another row into shopping cart items, and oh no, we got a blue screen. We've got an exception. Something crashed right in the middle of our transaction. So the database is left in this inconsistent state. But that's okay. If this all takes place inside of a transaction, no problem. If the database itself crashed, no problem. It wasn't committed. So the database is kind of holding this data in limbo, and since it never got committed, it's not going to completely save it into the actual database. So if something else went wrong in our program, maybe there's an exception or something, we can detect that and bail out and tell the database to roll back. So we're telling the database, forget what I said, go back to the way it was before. And I just want to, so then it goes back to like this. So I just want to make another comment here. If we went back to that first single table way, the data that wasn't in first normal form, if all of those columns were in there, not a good design, but if we went back to that, this would never be a problem. There would only be one insert, so it would either succeed or fail. No need for a transaction. Now, let's switch over to a NoSQL document database, which, to put it simply, is just you're storing data as JSON instead of tables, rows, and columns. So it's individual pieces of JSON. These are each called documents. Now, since my background is relational, and it actually is, I might try the same approach to storing data in a document database. And maybe it's because I'm importing data from a relational database, and so the data is already split up like this, so I'm going to leave it split up in my document database. Or maybe this is just because this is the approach that I know, and so why shouldn't it work the same everywhere? And if this is what you're thinking with NoSQL, and then you hear that there's no ACID transactions available, well then yeah, no kidding, you're not going to want to do that. But we aren't using tables anymore. There's nothing that says we have to put the data in third normal form. In fact, since we're using JSON, we have support for arrays and nested objects in a single piece of data. So if I want to create a shopping cart and model it like this, with an array of items inside the document, then it becomes a single operation on a single piece of data. So voila, ACID guarantees in a document database, as long as we're only working with one document at a time. So therefore, when you can model your data into a single document, instead of a bunch of pieces, you no longer need the equivalent of an ACID transaction. If you've read this book before, or heard about the concept of aggregate root, that's basically what we're doing here in a modeling exercise. We're trying to crunch down the data and join it all together into one piece of data, as much as we can, into aggregate roots. And I'm not the first person to make this observation, so Martin Fowler here, he actually created the term, tried to coin the term aggregate-oriented database, and this is as far back as 2012. And there's a link to this presentation where he talks about it right here. But it never really caught on. But it's really, in my mind, it's a really good way to think about it. Aggregate-oriented is kind of expresses the intent of what's going on better than key value or documents. Okay then, so if we can get past that, then let's talk about why are people using NoSQL in the first place. And I think this is important because this might help you, inform you whether NoSQL is right for you. So there's kind of the big four reasons, and there's lots of reasons really, but these are kind of the big four. And these all four may not apply to you, may just one of them might apply to you. But let's just go through them one by one. So the first one is scaling. And it's my belief that scaling was kind of the main reason that NoSQL started and gained traction in the first place. Because scaling is hard to do with systems that were designed to be run on one machine and serve a relatively small number of operations. And so serving millions of operations with one big machine becomes expensive or at some point becomes impossible. So what scaling actually means in practice to me is that it should be easy to have a bunch of machines and cluster them together and then split the data amongst them, which is called sharding. And that should be, built in and automatic. Now in practice, this varies from solution to solution. So depending on which NoSQL solution you look at, they may not be designed with easy scaling in mind. They may be designed with other things in mind besides scaling. So you may need to configure your own load balancer. You may need to do your own leader election, define your own shards, etc. So a lot of extra work there. It also means that in general with distributed computing, transactions become much more difficult because now you have the network in play. So therefore, early on, this is one of the trade-offs, the atomic A in ACID. Availability is another huge benefit of a database that's designed to be distributed. So back to that one big server model, if it goes down, the whole system goes down. But if you have multiple machines on the cluster, if one goes down, the remaining servers can recover and stay available. And again, in practice, depending on which solution you look at, this might involve having to set up your own sharding definitions again, internal and external replication processes, using a tool like Zookeeper, etc. Performance is a big reason. So every database claims superior performance, of course, and they all publish benchmarks to back it up. They can't all be right. But however, we've already seen an example of data modeling and consolidation that would reduce the total number of operations. Additionally, many NoSQL systems, not all of them, but many of them introduced a memory first or memory only capabilities, and memory is going to be faster than disk. So you don't have to wait on disk access or wait on it as much. This also factors into the lack of transactions, specifically the durability, the D in ACID. We're going to talk about that later. Now, in my opinion, data flexibility was never really the primary goal of NoSQL, but it is a very nice side effect. Or unfortunate trade-off, depending on who you ask. So each piece of data is isolated. It's on its own because it needs to be able to live on its own no matter which server it's distributed to. So it has to be, it may as well be in a useful, well-understood format like JSON, for instance, that has parsing libraries written in every language and every platform you can think of already. So I'm going to focus on document database today, but another key tenet of NoSQL is polyglot persistence. Use the right database for the job. So especially in distributed architecture or microservice architecture, where each service may want or need to take advantage of different kinds of data structures. So graph, search, time series, document, which I'm focusing on today exclusively, mobile synchronization, and relational, of course. So why is ACID so hard with the NoSQL system? Why don't we just have ACID there? So first we got to talk about what ACID actually means. And it's not just about transactions, but it's a whole set of properties for databases that was coined around 1983. It's not a standard in the sense that if you get two database people together, they're not going to agree 100% on what it actually means. There's no ACID governing body or anything like that. And there's a lot of nuance here. So from my point of view, it's more about having a conversation than it is about compliance to a standard. Now, I fully expect you to disagree with my characterization. That's totally fine, at least partially. But what I do want to review ACID, though hopefully you're already at least somewhat familiar with it before you came to this session, came to this video. So A is for atomicity, and this means that all operations that are grouped together in an atomic unit will either succeed or fail together. So back to that shopping cart example. And so with a document database, if you can model it down to a single document instead of two tables and 3 or 4 rows, you get atomicity already. So that's the equivalent of 3 operations in a relational database dropped down to 1 in a document database. And so as I mentioned, in a single document level, a NoSQL database can still have atomicity. C is for consistency. And in my mind, this is the most nebulous part of ACID. But let's think back to that shopping cart example. If an operation can't be rolled back, the data can be placed in an inconsistent state. So we could have half the shopping cart written to the database. But there's other things that might fall into this category that fall under the consistency umbrella. So with a relational schema, if you've defined a 5-column table, you can't put 6 columns worth of data into it. That's just not consistent with the definition. A NoSQL document database, if it requires JSON, then you can't insert a non-JSON string there. It's going to check it and say, that's not JSON, I can't accept that. Eventual consistency, something maybe you've heard of before. This describes a situation where the data you retrieve may not be the latest copy of the data. And this depends on a number of factors from database to database. So for instance, in Couchbase, there's a number of different ways to read and write data. If I use what's called a key value operation, so I have the key to a document and I use that to update some data, and then I use the key value operation to get that piece of data, it's always going to get the latest data. It's strongly consistent. However, if I use the key value to insert some data, and then I use a Couchbase SQL query, that's going to involve a secondary index. And if I do it right away, I may get some stale data, or I may get the latest data. It's going to depend on my latency preferences, because that index is updated asynchronously. And so if stale data is a concern for your use case, and sometimes it's not, but if it is, then you want to check in your NoSQL database, what are the settings I can use to make sure I don't get stale data back. And there's trade-offs to that. There's performance trade-offs for that. By the way, this is also true for relational databases. It's just that typically by default, you don't have to worry about that too much. But you can, of course, make changes to settings, and I'm not going to go into that, but you can get dirty reads out of SQL Server or MySQL as well. But I want to look at isolation here to show you why. But let's talk more about consistency. So this is the JSON consistency models map, and this looks really maybe confusing or a bunch of new terms you never heard of before. But let's just break it down by color here. Pink are the consistency models that are just not available when there's some network failure. So just not all the time, not possible all the time when you introduce network, which you have to in a clustered distributed database. So generally speaking, with pink, all the nodes must stop their operations to make that safety level happen. Orange is what's called sticky available. So it only works if your clients are stuck with a specific server in the cluster and you can't switch between them. So we don't see a lot of that, except in some use cases. Blue is what's called total availability, which means it's possible even when the network is completely down. So the way this map works is that read committed, for instance, is stronger than read uncommitted. And it means that read committed means that dirty reads are not possible. You can't read data right in the middle of a transaction. And read uncommitted means you can read data that's right in the middle of a transaction. So in Couchbase, as I mentioned, using that key value API, in our transactions, it's actually monotonic atomic view. It's the strongest level with the key value API. But Couchbase doesn't just consist of the key value API. It's not just a key value database. So when using other APIs, at least right now, for instance, we're working on that, but using other APIs, it's actually read committed. So it's a little bit in between the read committed and the monotonic atomic view. So it's not quite as strong as possible yet, but it is getting there. Now, you might say, oh, well, strict serializable at the top. It's the strongest, so it must be the best. Well, there are definitely trade-offs. And if a node shuts down, nobody else can do anything. And there's a huge latency trade-off there. So this is actually rarely used, strict serializable. It basically means one operation at a time. Not literally, because if there's some obvious way to know that two operations won't conflict, it'll allow it. But actually, read committed is the default for many relational databases, for instance. Isolation, so in regards to transactions, this is very much about concurrency. So trying to read the same piece of data or update the same piece of data at the same time from two different processes or more. So if a transaction is isolated, is properly isolated, that means it should appear to leave the database in the same state as if the transactions were executed sequentially. So optimistic and pessimistic locking are typically the ways you deal with this, and those have been available in distributed databases for some time. But again, at the single document level. Now, if we're talking about ACID transactions in a distributed database, the transaction may involve locking multiple documents. But there must be a timeout associated with those locks. Otherwise, a document's going to get locked in perpetuity. So therefore, the whole transaction is constrained to a timeout period. It has to finish within a certain amount of time, otherwise we have to cancel it. And the last one is durability, D for durability. Is the data durable? So after I write the data, if my system crashes, will the data still be there? Now typically this means it's been written to disk, but there's really more to it than that. Because what if the disk fails? So maybe we need a replica on some other disk, some other server perhaps. Or what if it's a memory-only database? Is that impossible for it to be durable? What if there's a copy not only in this server's memory, but another server's memory? Is that considered durable? What if the whole data center goes down? So it's not durable at that level. So we need a whole separate data center. Maybe we have a west and an east, for instance. And if one data center goes down, we got a copy in the other data center. And for all of these, there's a performance trade-off. Right? Because it takes more time to write to disk, to write to another node, to write to another data center. And ultimately, do you check? After you write the data, do you actually make the check? Or do you just assume that the database is going to handle it? And so do you check? What do you check? Do you check that it's been saved to one disk? Now you may say, I want it to be saved to multiple data centers, but am I actually going to go and check that? It's going to add a lot of extra time. So do I check that it's been saved to just one disk? And that's good enough for now. Or 2 disks, or 2 other machines' memory, or 2 other disks and memory, or 2 other data centers. So in NoSQL, you can specify the durability level on a per operation basis. So for this one, I don't really care. I'm just going to assume it's saved and it's fine. Fire and forget. For this one, though, it's a transaction of money. So I want to make sure that I check on 2 disks and 2 machines memory, for instance. And so that's something you can do on a per operation basis. And so in a transaction, you definitely need to incur that kind of overhead to verify the durability. Implementing ACID is already a challenging problem. But factoring in the nature of distributed systems makes it even more so. So here's just some of the problems in building an ACID transaction framework for distributed databases and some of the ways to mitigate them. Now, as a developer using a transactions API, it's not something you necessarily have to know, but it is really hard stuff. And so it may be a little bit behind the scenes of some of the challenges to actually building a transaction system for a distributed database. So one of them is a class of problems called split brain. So this is a network problem. If a network cable gets unplugged or something goes wrong with the networking where not all the machines in the cluster can be reached. So what happens if one of the machines in the cluster crashes? So the solution to this is a consensus requirement. So for this given transaction, what's an acceptable number of nodes for the operations and replicas to persist to? Kind of the durability requirement. Is 1 good enough? Is 2 a majority? So at a transaction level, you basically get to say, as a developer, what is strong enough for me for this particular transaction? What about uncommitted transactions? They leave sort of junk behind, right? So I'm making an assumption here, and this is because I'm going to be going through this as a demo, that the work's being done on the client side, not the server side. But of course, the server would have to clean up this stuff as well. But if the client itself crashes, it may leave transaction data staged and half finished behind. Now, those should never lead to dirty reads, right? Then we're not at the highest isolation level we can have. But the artifacts do need cleaned up. That stuff needs cleaned up eventually. So we'll see some of this in the demo. But there's a couple ways to go about this. One is the cooperative model, which is what I'm going to show you today. And basically that means even if my process crashes, there'll be another process along soon that'll clean up my mess for me. And there's something called a Paxos implementation, something like Zookeeper or a Paxos implementation to handle this on the server side, to kind of get things in sync and just sort of have an authority on the server to figure out, okay, to direct traffic and things. And edge cases, this is a huge one, identifying edge cases. And really the only solution to this one is mitigation. So you can spend a lot of time addressing hundreds of edge cases. What happens if a network cord is unplugged at various times during my transaction? What happens when a node comes back online? What happens if there's a network or disk corruption? What happens if we set loose a chaos monkey to start crashing things at random? And by the way, this is true for relational databases, by the way, but I think the only thing you can do is just keep identifying those edge cases, improving your transaction implementation, or you might say at one point, well, that's a 1 in a billion edge case. That might happen one time in a billion. So right now it's just not worth it. The juice isn't worth the squeeze, as they say. Latency. So this is a challenge here in that could affect performance. Because our NoSQL is designed to be scalable and performant, we don't want to just reinvent a relational database here. So the solution here is basically say, only imply ACID transactions when you need to. Just, sort of, it's an education issue. Developers should not, for instance, implement a repository pattern that wraps every single thing in a transaction, whether it needs it or not. So only use it when you have to, because there's overhead there. And basically, we need to know there how much is the overhead. How does an ACID transaction affect performance and high availability? And so again, the solution is kind of education. Use that in modeling with the aggregates oriented, with the aggregate roots as much as possible to solve, instead of immediately reaching for a transaction. So a transaction should be sort of like the second tier. Correctness. So once we've got what we think is a good ACID transaction system in place, how do we know for sure? And so how do we test that? And how do we verify those edge cases that we've identified? Because that's sometimes very difficult to simulate those situations. So one of the things we can do is we can solve this with what are called JSON guidelines. So I showed you that JSON chart earlier. JSON actually has a process that they'll take your system through to say that it passes the guidelines or not. But this is a challenge in and of itself, because JSON costs a lot of money to get their consultation. And it's a lot of work for both JSON and whoever's building the transactions. So at the end of the day, and you might find yourself in this situation, and I'm not trying to diminish a competitor here, but this just shows that it's very challenging work, and it's far from a completely solved problem. So the next thing you need to think about in a trade-off is, where do we do the actual transaction work? Is it client-side or is it server-side? Do we have the client, which could be Java, .NET, or PHP or whatever, do the transaction work and do all the coordination, or do we have it all taken care of by the database, by the server? Now, Couchbase has decided to take a completely client-side approach, which I think makes it stand out a little bit. So to a developer, this hopefully shouldn't mean very much, but it's worthwhile to explore the pros and cons of them. So with the server side, we've got some pros. The main pro is you don't have to change your SDKs very much. So basically, you're just relaying start transaction, commit transaction, rollback transaction. You're relaying those commands to the server, and the SDK isn't doing much work. Now, I don't want to diminish the SDK work, because there's still real work to design those and document those, but the actual implementation doesn't live in the client. That's kind of the main pro there. The cons is that you have to have some sort of global tool to manage the transactions, to coordinate them, to synchronize clocks. And this can be fragile. This can require configuration. It can have strict requirements about what servers you're running your database on. So client side is kind of the flip side of that, basically. And the pro is that you don't have to have any of that global coordination. It's really just to the server. It looks like regular operational traffic. So you don't have to make any changes to the server to do this. Now, there are some features that are necessary to make this happen. So durability features, staging capabilities, and things like that. But none of the transaction logic lives on the server. So this makes it quick to iterate, actually. You don't have to wait on the server team to make a change and then update the SDK, for instance. And it's actually very cool to see this in action behind the scenes at Couchbase. And then nothing on the server needs to be changed or configured. Again, it's just regular traffic as far as the server is concerned. So the cons is that each client needs some major additions. So not only just adding the new functions to begin, commit, rollback, but the actual logic there of how do we stage a transaction, how do we commit it, how do we lock documents, how do we time out, how do we run a background process to clean up after other sort of abandoned transactions. So all clients must be on the same algorithm. They've got to be on the same page when it comes to transactions. So this makes it a little harder for community contributions. So let's say someone wanted to build a Couchbase client for Fortran. Now, Couchbase Incorporated does not have a Fortran client. But if you want transactions, you need to, well, first you need to build the Fortran client, which is a lot of work as it is. But you also need to learn about and follow the same algorithm to build a transactions in Fortran. Or you can wrap a proxy some other client, like a C client, for instance. So Couchbase, the company, is going to do a lot of this work, but it's just a heavier lift in general. And this is kind of why you're going to see my demo in Java. It's not because I like Java. I really don't. I'm not good at Java. It's going to be obvious to you. But it's just Java is the most popular client, so that's where Couchbase started. And that's where proved out the concept there, and they're going to eventually roll that out to other clients as we go. So it's kind of a heavier lift, and this is kind of the con to it. Okay, so speaking of demo, I'm going to go and show you right now a transaction in a distributed NoSQL database in Java. But don't worry, if you aren't a Java developer, it's still readable. You can still understand what's going on as we go through the demo. So I've got a demo here, and this data used by this demo is to help me track conferences and my interactions with them. So I go to a lot of conferences and I do a lot of activities, so it'd be nice if I could track that. So there might be a momentum piece of data, momentum conference that I'm tracking. And interactions to that might include things like me submitting to the CFP, the call for speakers, getting accepted or rejected, actually delivering a presentation like I'm doing right now, answering questions afterwards, submitting slides, and other kinds of follow-up. And so I want to track all that. And I need transactions for this because I want the one piece of data, the conference, to contain information about my latest interaction and the total number of transactions. Now, I could do this with a query each time and a join, but it's going to be slower, one. And two, I wouldn't have anything to demo for you. So let's get right to it. Here at the start, I'm just defining some strings. It's not really important what they are, but just some strings I'm going to use throughout the demo here. Let's go down to a main here. So inside of main, I first connect to a Couchbase cluster. I'm getting a bucket object, a collection object. And the details here aren't super important, but basically I'm connecting to a database and getting some objects to interact with the data. Next up, I'm setting up two initial documents. So I should only have to do this once, but I'm running it every time just to make sure that they're there. And let's scroll down and take a look at this method. So one document being created is a document to represent a conference. So again, a document representing momentum. And there's another document representing interactions. So individual events that I perform for and during and after momentum. And there's none yet, so it's an empty array right here. Okay, so let's go back to main. Now I'm going to set up a transactions object. So this is Couchbase specific here, but I'm setting up a transactions object, and this is what I'm going to use to start a transaction. Now I have the durability level here set to none because my demo is only using a single node of Couchbase. In production, I'm going to have multiple nodes, so I can choose to set to a different durability level. Now this goes back to those trade-offs. So what do you want to consider to be durable enough? So is it going to be a majority? Majority of the nodes have the data, or backup copies of the data. Is it a persist to majority? Basically, you want to confirm that a majority of nodes have the data and have it written to disk. Is it a majority and persist to active? So we want to confirm that most of the nodes have the data and the active node, not the backup copy, but the active node has been written to disk. These are all different levels. It depends on a number of factors. So what's your risk model? What's your cluster size? And so on. And now after creating this object, I'm pausing for the user to press enter. I'll show you why in a bit. So let's scroll down a bit to actually start the transaction. So notice here a transaction.run. This contains a lambda, I assume that's what they're called in Java, and a parameter of CTX. And that's the transaction context. And that's what I use to interact with the data while I'm inside of a transaction. So I start by grabbing the two documents that I already initialized. That's ctx.get. And I then get their content as JSON objects. So my knowledge of JSON and Java is a little shaky here, but I'm putting the data into JSON objects so I can manipulate that data here in Java in memory. Scroll down a bit more. I'm updating the conference document by incrementing the number of follow-ups by 1, the number of events by 1. And I'm setting the last interaction date to now. This is inside the conference documents. And so then I'm updating the interactions document by adding one new event to it. Because I'm increasing the number of follow-ups by 1, I'm adding one new event. And this is me submitting to the CFP, which is typically the first thing I do interacting with a conference. So let's scroll down. I'm going to skip this commented stuff for now. I'll scroll down a little more, and here I'm using the CTX object to take those updated JSON objects and replace them in the database. And so the data in Couchbase for those two documents is going to be updated. Now at the end of this lambda, the transaction is committed automatically, or I could say ctx.commit explicitly if I need to within that code. Okay, so that's it. So let's take a look at the Couchbase data right now. You can see this demo bucket is completely empty. I've done nothing with it. It's just no documents in here. Okay, let's go back to Visual Studio. I'm going to run this console program. So here at the console, I need to press Enter to continue. So at this point, I'm going to switch back over to the Couchbase UI and show you what data is in there. There's a momentum document and a momentum interactions document. And there's also these _txn documents, which is some of the data that the transaction is using to keep track of things. In the future, these documents will basically become hidden metadata, but for now you get a little peek behind the scenes. So let's examine these two momentum documents. So momentum contains the basic information about the conference and nothing else. The other document contains some information about which conference it corresponds to, so kind of like a foreign key, and an empty array of events. So I've done nothing with that so far. Okay, let's switch back to the Java console, and I'm going to press enter, and there we go. So the transaction has run, it's now finished, transaction complete. Let's go back to the Couchbase UI. And let's look at the momentum interactions document first. See that the event array is no longer empty. It contains my CFP submission and the date of my submission. Let's switch over to the other document. It now has a follow-ups field. It's brand new there, and it's 1, because I only have the 1 so far, and a last interaction, which matches exactly the date of my CFP submission. Okay, let's try something else. Let's go back to the Visual Studio Code here. I'm going to uncomment another interaction, this time for delivering a presentation. So just kind of the same thing, but different information here. I'm going to run the program again, and I'll just press enter this time directly. So let's go back and look at the data. Momentum now has 2 follow-ups and the new last interaction date. And if we look at the other document, it now has 2 items in the events array. So you can see why a transaction is important here, because I want to update them both so that they stay in sync. This is all great and all, but it's assuming that nothing goes wrong, that we don't get that blue screen I showed earlier in the presentation. What happens when something goes wrong right in the middle of the presentation? So let's go back over to Visual Studio Code. I'm going to uncomment the third item here, which is answer questions on Slack. So after the conference, I can answer questions on Slack. But I'm also going to uncomment this throw new exception statement, which happens before the transaction gets to the commit. So what's going to happen when running this program? All right, so we'll run the program, and I'll press enter here, and oh, there's an exception. Oh no, right in the middle of the transaction too. So what actually happened to the data? Let's switch back to the UI, Couchbase, and look at the Couchbase data, and we can see that it's in a consistent state still. It's as if the data was exactly the same as it was before the transaction started, which is exactly what we want. So that exception happened within that transaction lambda, so it could handle it. No problem. So that's good. That's what we want from a transaction. We want consistency there. Let's peel back the curtain a little bit more and see some of the messy details behind the scenes. So let's go back over to Visual Studio Code. I'm going to comment out that exception again, but this time, notice that I've set a breakpoint right here at the second CTX replace. So I'm going to run the program again, but this time in debug mode. Okay, so running in debug mode. I've hit the breakpoint here, and now what I'm going to do is I'm going to kill this program. Just kill it right in the middle of a transaction. Not an exception, just straight up kill the process. So what has happened to the data right in the middle of my transaction? Let's switch back to the Couchbase UI. Let's look at the momentum document, the one that has been updated up to this point, according to the transaction. But look, the data is still consistent. Good. That's what we want. It's read committed. But let's look at the metadata tab this time. And there's a whole mess of data here in the X-adders section. And you can see that there's some staged data. So we've staged the data that we want to update here in the document to have 3 follow-ups and a new last interaction date. So our data is meeting that read committed criteria, but it's left some mess behind in the staging data. So what are we going to do about that? So it's no problem. Let's switch back to Visual Studio. The client-side approach here, the cooperative approach here, is going to clean up any messes left behind by previously uncommitted transactions. So I'm just going to run the program again, and just by instantiating the transaction object, I've actually kicked off a background process that's going to clean up leftover data that expires after a given timeout. And that you can adjust that. It can be longer or shorter, but I think it's a minute by default. So I'm going to wait here at the press enter prompt for a minute. I'm actually going to fast forward the video here so we don't actually have to wait that long. So after I press enter, the transaction then proceeds as normal, and that metadata will be overwritten and cleaned up shortly thereafter. And just to show this is the case, let's switch back to the Couchbase UI one more time. Show the momentum document and its metadata, which now has an empty X-adders section. So all that stage data, that mess, has been cleaned up. So what I just walked through here is one of those edge cases. It's not an exception, it's a process dying. So now apply that to the process dying elsewhere in the execution. Or one of the Couchbase servers dying in the middle of the execution. Or failing over. Or split brain of some sort. And you can see that there's a lot of edge cases that will hopefully rarely happen, but many of them do need accounted for. So that's it for the demo. Let's go back to the slides and finish up. All right, now back to the slides. Let's review here. ACID transactions, it gives you the ability to treat multiple operations as a single all or nothing operation. The trade-offs here is that basically use only when necessary. Don't use a repository pattern that wraps everything in a transaction by default. Target specific areas where you need it. Because remember, there's overhead, whether it's a two-phase commit, enhanced durability, whatever. There's more overhead here, no matter which approach your NoSQL database is taking. And so solve with data modeling when possible. Use an aggregate-oriented approach as much as you can, and consolidate as much as possible to avoid the need for a multi-document transaction. But in the end, don't be afraid to use a transaction. They exist for a reason. It's a tool, it's a safety net, but don't lay in it like it's a hammock. Transactions in NoSQL are on the cutting edge, and they're still evolving. So what I just demoed for you was the Couchbase key value API using a transaction. So this means you can start transaction, perform CRUD operations, insert, update, and reads of documents using their keys, and then commit. However, at this time, if you're using Couchbase's SQL API to run queries, you won't get a dirty read, but if you want to use SQL to make changes in a transaction that can be rolled back, that's not yet supported. So that's another hard problem that Couchbase is currently working to solve. I want to show you some other NoSQL databases that are also have created some ACID transaction efforts. So this first one is Mongo. It's not 100% clear yet how all the details of Mongo transactions work, at least not to me. So there's some things like they've mentioned Lampert clocks for timestamping operations. This is kind of done. So Mongo's using the server-based approach. And so since clocks are on multiple servers will never be perfectly synchronized, Lampert is a way to provide some ordering there. And it's also using gossiping, what they call gossiping, to check to verify changes have been disseminated. So again, it's not clear what exactly that means, what disseminated means, and how that works. But certainly, if you want to check out the white paper there, if you want to dig into those details, you can go and read through that on ACM. Other ones, so Cosmos DB on Microsoft Azure. It used to support only stored procedures for transactions. Now, as I said earlier, NoSQL is continuing to mature, and now you can use a transaction batch, what they call, from your own client code. So it's limited to a one partition key, which is basically how Cosmos groups data together to spread workload around. So that may be an issue depending on your use case there. It's also limited to 2 megabyte transaction over 5 seconds, so back to that timeout again, and 100 ops is the limit per transaction batch, which seems very reasonable to me. Again, going back to my earlier recommendation about only doing this when you have to. And another one I want to mention, since it's not NoSQL, but it's a relational, what's called a NewSQL, distributed relational database, is CockroachDB. So I want you to think back to the example about why transactions are even more important for a relational approach, because you're going to split data up into all those different pieces. So Cockroach is kind of inspired by Google Spanner, and it's all server-side implementation, because Cockroach wants to take the approach of being compatible with Postgres drivers. So you really can't go through and change the Postgres API, so you have to implement it all on the server side. So you have to worry about clock syncing here as well. If the clock skews outside of a limit, the database can just stop, like I mentioned earlier in the presentation, which obviously can hurt availability. And if you're using their cloud-based offering, this may not be as big of a concern, but if you're running on your own data center, for instance, this is something you have to worry about very much. And there's a video here you want to check out, specifically at 13 minutes, 42 seconds in. They start talking about transactions there. That's another great resource for you to explore if you're interested in that. They say you only remember 3 or 4 things vis-a-vis any given presentation, so here they are, Neo. You may not need transactions as much in a NoSQL setting as you do in a relational setting. The answer may be aggregation, consolidation, and not trying to take the exact same approach as you do with relational. NoSQL is maturing. This session is about the rise of ACID transactions in NoSQL. There's also been tremendous advances in other aspects of NoSQL: security, integration, reporting, analytics, deployment, etc. So if you've dismissed NoSQL in the past as being immature or not ready for prime time or not a fit for your projects, I believe NoSQL is now worth a second look. And the answer to NoSQL is, to why NoSQL is still expanding. The reason that exists in the first place still applies. So trade-offs to increase scalability, high availability, and flexibility. But now that NoSQL is maturing, the answer is expanding as well. High availability, scalability, flexibility are still even there when you need some ACID transaction capability. If you want to go down the rabbit hole even more, definitely start with JSON. You can check out the consistency model there. This video by Graham Popel is one of the very bright Couchbase engineers who's worked on transactions. He's got a full video here about it if you want to explore that some more. I wrote a blog post on ACID a while ago. This is before Couchbase even introduced transactions, because I wanted to convey that ACID is something that's not just about transactions. Couchbase publishes a huge number of benchmarks, and this link goes directly to the transaction portion of the benchmark, so you can kind of see the overhead that you're inducing there and what Couchbase can handle. High availability transactions white paper is there if you want to dive deep into the challenges. There's also a transactions design document, again, for the really deep details about how Couchbase transactions are supposed to work. Let's continue the conversation about NoSQL. Here's the ways you can reach me. I'm on Twitter as mgroves. I stream on Twitch on a regular basis. Matthew D. Groves. It's very interactive. It's not a webinar style session. You come into Twitch, you hang out, we'll do some coding, we'll discuss, answer questions. It's great stuff. So come and hang out with me sometime. You can email me at my personal email address there. It's me@mgroves.com. And you can find my really lame attempt at Java coding here on GitHub. So that's github/mgrove/don't-drop-acid. Also, there's a free event coming up, and it's this very week, the same week as Momentum. So if you're interested in NoSQL, you should sign up for this event happening later on. Lots of great content for developers across all languages and ecosystems. I've also heard there's some great swag and prizes available. This is totally free to sign up. And if you use this link here, this is my special link. My boss said he'll buy me a pizza for each person who registers. So I need some pizzas. Let's get signing up. I'm just kidding about the pizza. All right, thank you very much for watching this video. I hope you enjoy this, and make sure to check out the other content here in Momentum. And thank you very much for watching.